Hello, my name is Aditya Jadhav, and the topic of my project is crash analysis of a Ford GT body. The motivation behind doing this crash analysis is because I am interested in crash analysis and I was looking for uh, projects to do on crash analysis. So I was looking for projects for various other automobiles, but I could not find anything on a Ford GT bodies. So that was the reason why I chose this project. It was also hard to find data for Ford GT bodies because Ford did not make the product data public because of the product data confidentiality. So yeah, that is something that really motivated me to do that. And who are the other organizations that might also be doing it? And they for sure do it. So it is NHTSA, Global NCAP, and independent researchers that determine the safety of the vehicle during a set period of the year or number of years. So the purpose of my project is to analyze the behavior of the body deformation stress strain using different materials under crashing forces and determine their crashworthiness. As I said, my objectives are to determine the stress, strain, deformation of crumple zones, effects of using different materials. Now, as you can see that this is my finite element model and the geometry. So the dimensions of the wall are given, the dimensions of the mock model are given. The thickness of the car body for this analysis purpose is considered to be 2 millimeters. The mesh size is considered to be 15 millimeters. With the mesh size being 15 millimeters, the number of nodes after meshing that are generated are 10,184 and number of elements are 9,200. Then the types of elements used are tetrahedrons wall and quadrilateral for the car body. Now quadrilateral elements are used because quadrilateral elements help in better dissipation of energy throughout the body. Governing equations, in order to understand crash from a physics point of view, we can just employ two basic equations, which are kinetic energy equals to 1/2 mv square and work equals to force into distance. So the force that is being generated is the force that is being generated is the force that is uh, applied on the vehicle by wall because of inertia, and the distance for this physics or distance for this analysis can be calculated as the distance that the front front body crumples plus how long the vehicle rebounds after crashing. So this is how the work can be calculated, and hence the energy that is being generated during this process has to be dissipated around the passenger or the occupant so that it ensures uh, safety of the occupant, which is of prime importance during these phenomena. So yeah, so this is so the main goal of doing this is to dissipate energy around the occupant and not to the occupant, which can be harmful. Now, uh, coming to the solver part, this crashing phenomenon can be considered as a case of transient dynamics, which is time dependent. So for this, the equilibrium equation can be considered as given on the slide, which is m into second derivative of velocity plus c into first derivative of velocity plus k into u plus external force into time, where m is the mass matrix, c is the damping coefficient, k is the stiffness matrix, and external force is given by Fext, and t is the time. So what the solver does when you're trying to analyze a crash on any analysis software is try to solve this equation over every element that is being generated after you mesh the element. So once the solver tries to solve these equations over every element, we can get the results for stress, strain, deformation, and other characteristics if you would like. So this is how the entire simulation part plus physics part is for crashing. Boundary conditions. The boundary conditions for my analysis are that the wall is fixed at one end, and the car is given the velocity of 17881.6 millimeters per second in the negative x direction, which is towards the wall. This velocity roughly converts to, sorry, 45 miles per hour, and this is the standard testing speed used by NHTSA and IIHS. These are the material properties that I intend to use for my analysis, which is first material is aluminum alloy, and the second is titanium alloy, and these two materials will be applied to the car body, and their stress and strain results will be studied and compared, and the material of the wall remains constant, which is concrete, which is linear. Now, moving on to the results part. So, first I will be discussing the nonlinear aluminum alloy for the car body. This is the total deformation that occurs during the crash. So, the maximum deformation that can be seen here is 62, around 63 millimeters at 45 miles per hour. And these are the von Mises stresses. As you can see that the stresses generated for this are very high. So these are the results for the stresses that are being generated, and this is the strain. So this is the change in dimensions, or change in the form of the material that is being taking place. So yeah, so the maximum here that can be seen is 0.4758 millimeters per millimeter. So yeah, and this is the stress versus strain curve. So as you can see that this curve does not obey linearity. You can see that the curve is pretty much non-linear, which is what we were trying to establish. Uh, then again, let's move on to non-linear titanium alloy. So these are the results for the deformation of the non-linear titanium alloy, and the maximum deformation that can be seen is 108 mm. And these are the animations for the titanium alloy. Von Mises stresses, the stresses that are being generated during the crashing are 1855.1, and these are the animations for it. And the strain that is being generated is 0.8129 millimeters per millimeter. And these are the animations. Again, as you can see that the behavior is non-linear, what we were trying to establish. So after looking at these two results, I have taken the average values for elastic strain and average stress for nonlinear aluminum alloy and nonlinear titanium alloy. Now, as you can see that the elastic strain for titanium is high, and the elastic strain for aluminum is low. And for average stress, if we see that for average stress the titanium is high, and for aluminum it is a bit low. Summary and recommendation. This project was an attempt to reveal and compare the performance of different materials used for a car body by the way of visualizing the deformation and stress strain characteristics under testing conditions. The study can also be used for conducting a trade-off study for material selections for automotive applications. Trade-off study. So if we look at this, so if we consider the average stress criteria for performing a trade-off study, we can say that yes, the although titanium is is highly priced, uh, we don't necessarily need titanium for it. We can also make do with aluminum for our car bodies, so which is also cheap, and although it does save weight, but it also depends on what type of applications you will be employing titanium material for. So yeah, so this is an example of trade-off study that I want to talk about. And future scope for this project would be to perform analysis with a high density mesh and increase computing performance to observe the holistic view of the material behavior under crash conditions. And variation of thickness of the car body could also yield different results. So my experience performing this project was I was really limited by the computing power of the university computers because I tried remeshing a lot. So as you remesh, your density of your number of elements increase, hence your density increases, and hence the time required to perform the crash analysis increases extremely. So what I have done is I have went with a coarser mesh to save time and to get near accurate results. But if we wanted accurate results, we can have finer meshes. We can have increased computing performances to observe the materials accurately and present accurate results for analysis. And even if we also play around with thickness, we can see that there can be different results that can be made, which remains to be the future scope for my project. Thank you. And these are my references.